Hey everyone, today we're going to be talking about projectiles that are fired at an angle compared to the horizon, whereas before we were looking at projectiles that were fired horizontally or parallel with the horizon. An example of this would be a golf ball, a missile that's being launched from Earth, moving up and falling back towards Earth. A kick football, cannonballs, if pirates is your thing, are all examples of objects that are projected with an initial velocity that is angled at some angle above the horizon or above the horizontal or x-axis. These types of projectiles are going to rise off the ground and fall back to the ground, and they follow a parabolic trajectory as they rise up and fall back down. And basically, this motion, in almost all regards, is mirrored from the highest point of the trajectory back down to the lowest beginning point or the lowest ending point. So what happens in the first half of motion is mirrored on the second half of motion as well. And we study this motion by resolving initial velocity into its two components, horizontal and vertical components. And then we can kind of look at the motion of the golf ball, missile, football, cannonball, whatever it is, in two dimensions, in the x and in the y, but we're going to treat those separately. Now we know if we ignore air resistance, which we always do in this class, the horizontal component of our velocity of whatever object we're dealing with is going to remain constant. We'll ignore air resistance, we'll ignore the forces that are going to be slowing down the projectile, so we can study in a perfect world what this motion might look like. The vertical is going to be a little bit different. The object's motion in the vertical direction or in the y direction is going to be accelerated, negatively or positively, or accelerated and decelerated due to the force of gravity. Which, remember, g is 9.81 meters per second squared. Now as we look at a projectile's motion, we're going to use our vector components here. If we consider an object moving with an initial velocity at some angle above the ground, we can separate that initial velocity, as long as we know the angle, into its horizontal component using vi cosine theta, or into its vertical component on the y, where we have our initial velocity in the y is vi sine theta. Now when we look at these types of problems, we can rearrange one of our equations. Vf equals vi plus at. We can solve that for time, where we get Vf minus Vi over A. And this is what we're going to want to use with these types of problems. So we'll look at this typical motion of a projectile at an angle. We'll break down in two dimensions our velocity, vertical and horizontal, and what time will look like at different positions along the trajectory. So we're going to call this position 1. At the top of our trajectory, we'll have position 2. And at the bottom here, we're going to have position 3. So if we consider, let's say, a golf ball being projected with some initial velocity, we can look at the vertical component of the velocity. We can look at the horizontal component of velocity. We'll break this down in a second. As the golf ball travels and reaches its highest point, all of the motion of that ball is in the horizontal. At the highest point there, our velocity in the y direction is 0. Because as a ball is fired or hit with some type of initial velocity, it's traveling up its trajectory and it's being slowed due to the speed of gravity. Since gravity is acting downwards and our velocity is acting upwards. Up till position 2, where the velocity would equal 0, as it's slowed up to its point there by gravity, and then accelerates back downwards towards position 3, mirroring the motion from position 1 to position 2. So position 2, the vertical component of velocity, v of y, is 0. At position 3, we have a final velocity. I'm going to make that a little bit longer. We have a final velocity, and we also have a final velocity in the y, and a final velocity in the x direction. Now, to kind of break down time for this golf ball scenario, position 1, at the beginning of this motion, our time is 0. Now our initial velocity, whatever it is, let's say 10, 20 meters per second, that's going to slow at a rate of 9.81 up to the top of the trajectory where the velocity in the y will be 0. So our time can be represented by the initial velocity in our y direction, vi sine theta, divided by the rate of acceleration. This will tell us how much time it's going to take for that velocity to reach 0. And since that motion is mirrored, the time at position 3 is simply twice of what it was at the top of the trajectory. So we take position 2 and we multiply it by 2. Looking at the vertical component of velocity, the initial velocity, getting kind of run into here, the initial velocity in the y direction, if we break down that vertical component of our initial velocity, would be vi sine theta. And we would have to know the angle there in order to do this. At position 2, there's no velocity in the y direction. It's all in the horizontal direction. It's all in the x-axis. And the final velocity in the y would be the negative in the opposite direction of what it was from position 1 to position 2. And that's because it's moving in the opposite direction. It's moving back towards the origin of where the golf ball started. Now, this isn't really listed on here, but I'm going to put it on here. Talking about vertical components, acceleration at position 1 would be minus 9.81. And that's going to be the same for position 2. And as you probably saw from your projectile motion simulator, this does not change. So that's indicating that acceleration of gravity pointing towards Earth is always going to be counted as our negative direction. And that's why we see that negative velocity show up in position 3 when talking about the final velocity in the y direction. Now we look at the horizontal component of velocity. At position 1, position 2, position 3, our velocity in the x direction doesn't change. So at all positions 1 through 3, our velocity is going to be the horizontal component of our initial velocity, or vi cosine theta. And the acceleration in the x is going to be 0, because that's the scope of this course. That's all we deal with in all positions. No acceleration ever that we deal with in the x direction. Now the horizontal distance from where we start to where we end here is what we call the range. Horizontal distance traveled by a projectile. To me, that seems to fit a little better with a missile. I guess it could go with a golf ball. The range that you can hit the golf ball, how far you can hit it from position 1 to position 3, or where you start to where you end. This point here is important for any given velocity. It doesn't matter what it is. The range is going to be maximum. We can achieve the farthest distance in the x when theta is equal to 45 degrees. Now, as long as we keep the speed the same, complementary angles will have the same range. So if we think of, let's say, an initial velocity of 10 meters per second of a golf ball, we'd get the same range if theta was 20 degrees or 70 degrees. One's going to be a little bit steeper compared to the other, or a lot steeper. But we're just changing where our initial velocity is as far as being more in the vertical or more in the horizontal, but it's going to give us the same range. And that's for complementary angles. The actual range of a projectile is going to be shorter than the calculated ideal range, which is what we deal with, and that's due to air resistance, which involves a little bit more complicated math that we don't quite dive into within the scope of this class. So we'll look at a first example here. Small missiles fire with a velocity of 430 meters per second at an angle of 35 degrees with the ground. After a total flight time of 47.2 seconds, the missile returns to level ground, and we're going to ignore air resistance. So what I like to do, first is to draw a simple sketch of what's happening here. I'm going to use my little cannon. There's a missile being fired out of here. With an initial velocity. And we can break this up into horizontal and vertical components. This is going to follow a trajectory here from the ground until it returns back down to the ground. Now we have here the distance in our y direction. We have the distance in our x, which is also called the range. This will be our question C. Maximum height of the missile here, d of y, is going to be our b. And we can determine the horizontal and vertical components, which will be A. Now these are the few things we're going to solve for. Now I'm going to do a little known and unknown chart. Now looking at this, we know that initial velocity is equal to 430 meters per second. The angle that missile is being fired is 35 degrees with respect to the ground. The time that missile's in the air is 47.2 seconds. We know that the acceleration in the y is going to be minus 9.81 meters per second squared. This is acting towards the ground, and our motion is going to oppose that and then work with that. We know acceleration in the x is always going to be 0. What do we not know? We don't know the x component of our initial velocity. We don't know the y component of our initial velocity. We don't know the maximum height, or the d of y, of the missile. And we want to find the range, the horizontal distance of the missile. Now the first part of this, A, should be hopefully relatively straightforward. We want to determine initial horizontal and vertical components of velocity. And in order to find the horizontal component of velocity, we want to use VI cosine theta. And to find it in the vertical, we're going to use VI sine theta. So to start off, the initial horizontal component is equal to our initial velocity of 430 meters per second times the cosine of 35 degrees. This gives us an initial horizontal component of velocity of 352 meters per second. Now that's just our x components. We want to do the same thing for the y. VIY is equal to, again, the same initial velocity, 430 meters per second. We're going to use the sine of 35 degrees. So we'll determine how much of that 430 is in the vertical. So the initial velocity in the y comes out to 247 meters per second. So we broke up our initial velocity of 430 meters per second into its vertical and horizontal components. B is slightly more complicated. We kind of got to think about the motion of this. What's happening here? We're looking for the maximum height of the missile above the ground. Now we know that, I want to think about the time here. The total flight from ground to ground, from beginning to end, is 47.2 seconds. The time to the peak is halfway through our motion, so it's going to be 1/2 of our total time, which is going to be 1/2 of 47.2 seconds, which will give us a time of 23.6 seconds. And this is to rise to peak. So it's going to take us 23.6 seconds to rise from the ground all the way up to the maximum height that this missile will go. So in order to figure out, there's a couple ways we can do this. I'm going to show you one, I'll show the other few in class. We want to find the distance in the y direction, which we can find by looking at the average velocity in the y times how long it took the missile to rise to its highest point. So we're kind of thinking about half the motion here. We know that at the highest point, the velocity in the x direction, or excuse me, the velocity in the y direction is equal to 0. So to find average velocity, we know that that's VI plus VF over 2. So we get our initial velocity, and this has got to be in the y direction, so we're going to want to use the initial velocity in our y direction, which will be 247 meters per second, plus the final at the peak, which is 0 meters per second. We're going to put that all over 2. It's going to give us 123.5 meters per second. Now that we have the average velocity, now we can plug this in to solve for the distance in our y. So the distance in the y is equal to the average velocity in the y, which we found to be 123.5 meters per second. That average velocity happens over a time of 23.6 seconds. So these are lining up here and here. And this comes out to, after we round, 2,410 meters. And that's equal to the distance in the y direction. So the maximum height that that missile will reach is 2,410 meters. Two other ways we can do that. One is using distance in the y, our distance formula, equals the velocity in the y times time, plus 1/2 acceleration in the y, t squared. The other one we could use, since we know each of these, vf squared equals vi squared plus 2ad. And again, this would be in the y, in the y, and in the y. Either of those three will work, depending which one tickles your fancy. Last part I'm going to show you here is for step C, where we are going to try and find the horizontal range of the missile, or the distance in our x. Now this is similar to the one before, where to find the distance in the x direction, we want to use the average velocity in the x times the time, but we want to use the total time. So not just the half the time, or the time to rise to the peak of the trajectory, but the time from launch to the time to land. Now we know the average velocity in the x. We get this here. We solve for that in part A. So this comes out to 352 meters per second. And we know that the time total from beginning to end, which was given to us, is 47.2 seconds. This is the distance of our x, or our range. This comes out to 16,614.4 meters, which will round to 16,600 meters. So that would be the range there of our projectile. We'll do some more practice with this in class. Come in with some questions, and best of luck. Have a great day.